Welcome to a new test and teardown video. This time it's another oscilloscope, also from Gould. This one is not just a random one of them. Oh no, this is the special digital storage oscilloscope OS4000. And I think this one is an optional add-on module. It looks like it is in its own little case here, so maybe you can take this off. So this is an output unit, so it's probably able to replay or recall memory, and you can put in an analog oscilloscope here and then replay this on this unit. I think that is how it should be able to do, right? The oscilloscope itself is only a 10 megahertz analog oscilloscope, 2 channels, and the digital part is 8-bit, 1 kilo of memory, and it can only record 450 kilohertz, or did they say it's usable up to 450? So that's probably just a few samples at that speed. I don't know if I expect to get this up and running. As you can see here on the front, it's really nasty, and this is just the corrosion you see here on the front. Look at that. It's really badly corroded. It was stored in a place where it could rain on it, and oh, look at that. It's just so corroded all over the place. And here comes the shocker. So this is the side of it. I actually just took it home to pull it apart just for the fun of it, because this is really a special analog digital scope. So hopefully it's going to contain all sorts of cool things. Yeah, let's start to open and investigate its mental condition here. I don't know. We got a few things that's not working. Oh, I can't even turn half of these. Yeah, oh, nice. Oh, this is super nice, but this one is just, yeah. Oy, crusty. Yeah, but this is what happens when people don't store stuff correctly. Sad. So this is the back. Oy. So how is this module connected? Is this connected to digital output? But there isn't any interconnect here. But it really looks like this is something. So this is just tricks. This is just a design thing. It is, of course, completely integrated with the scope. Yeah, there's no way out of this. I have to open everything. Oh, I just can't get myself to open and see what will I expect. It is, of course, a little bit of a sad day. This one is definitely super crusty. All over the place. It's full of mold and full of corrosion. But if we just try and pretend like we don't see any of this, then it's just, you know, fun to see how stuff was designed back then. I really don't expect to be able to power this up. I mean, no. So, but I find some really cool design choices here. Look at that one. So this is a precision voltage divider. They're normally used for voltage voltmeters and such, right? But this one is used in a time base for all the different speeds, and then you get accurate time base settings. So that's pretty nice. It is, of course, very much full of digital ICs. I think they said 1970 something. So still quite early for a digital oscilloscope. But look at that. All those ICs, it's probably some memory and storage, playback, all that kind of stuff it can do. It also got roll mode and all these fantastic features that we are so used to today. See, that will be deflection amplifier running at high voltage. Look at the resistors for the high voltage deflection, just super, super corroded. See, I repaired the on-off switch, added some contact 61, and then a few seconds later, it of course works in the little clickety-clackety. And there's another little really big problem with this unit. I think we got 4 or 6 large red capacitors hidden in here. I think this is more or less the whole power supply, rectifiers and all that kind of stuff that is hidden behind down here. And let me see if I'm able to show you. Yes, here you can see now that is the corrosion going through the plastic of that red capacitor. And this is how they all look down there. So I mean, is this only a little cosmetic detail on the outside, or is it the acid from the capacitor that's like coming all the way through them? And that is not good at all. So I think that should definitely prevent me from power this up. At least I should expect this will blow the fuses and stuff like that. So I will take my precautions. It could be fun to see if it's only a little cosmetic thing. I will go around and see what else I can find of stuff. See here, it's really badly corroded and super dirty. Everything I touch, I just get so, yeah, you can imagine when it looks like this. Let me see if I can get a little bit of light in here. That is the state. That is the rear side. I mean, there's a super huge circuit board occupying the whole rear side. And that is the corrosion on some of the capacitors. That's definitely deflection and focus and all the high voltage stuff. And that circuit board there is really ugh. Oh, nice and clean right there. So that is the bottom of the unit and the playback. I don't know if this is really the playback unit, but I would think so, because it's connected to the digital output and it's connected to, see, that will be all the playback B and C connectors, and that will be op amps for doing that. So that is probably just access to the memory. That will be the big board with all those ICs. That's of course the memory, so you can play back analog output from that memory. So that's pretty cool features. And that board here looks quite all right, but the ICs down there, look at the corrosion on the ICs. That's really sad. Well, maybe we should just try and power it up and see how much it blows up, because I can't do a lot. This is just a too big a restore project. I mean, I just took this from the container instead of putting it in the container. So this, I'm just delaying the time to throw out kind of thing. This is at least how I feel at the moment. Until I see a beautiful screen and a beautiful trace and super sharp and nice and stable behavior, yeah, okay, then we can take it from there. Just for the fun of it. So I think everything is in the middle, except for that one, right? Channel 1, la 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 la. All these, more or less. What else can we do, right? Yeah, this is the position of the two channels. So I think we're just gonna leave everything here in the middle, and let's try and power it on. Okay, so I turn on mains, and nothing bad happens, and then I push this button, and we see 80 watts, 70 watts, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 130, 140, 150, 160, 170, 180, 190, 100, 110, 120, 65 watts is completely normal. I would expect to see we don't see any pictures at all. So where is the hello? Where are you? Is it just position? No pictures so far. Aha, run. I don't know what to do here. Start, stops. But it looks like it's at least. What are we doing here? Come on, man. Let's see a little bit of a tiny. I mean, look at that. We get all sorts of lights and lamps and responses. I think I really did deserve to see a tiny little something, right? Ah, come on, so man. At the back, that's of course all the power supplies and all that stuff is going on here. You can actually read on the circuit board the different voltages. And then I went through all the different voltages and they're all perfectly fine. We don't show that one. So this one is supposed to be 170. It's clearly written. How about that? But all the voltages, they're perfectly fine. So why is this thing not working? Of course, we got a few extra voltages in this area. That is a little bit nasty. You don't want to just poke around with a meter like that up here. But that will be the deflection. And that can also cause the picture to be out of the way. So you'll see deflection here. Yes, 140. So that is quite normal. I would expect both of these two to be almost the same voltage, because that is the same kind of deflection. See, this one is probably the horizontal, and that one here is the other one, and that one is also in 120. And yeah, see, this one is normal. Here I have them at about the same voltage, and the other deflection, there's 170 and 140. So that difference could actually mean the beam is outside of the screen. So I think I will follow this wire and figure out what kind of deflection is that. Another thing you want to do is you want to see if you dare to go as close as I do here and have a look down there. You see, that is actually filament glowing. So that is also a good sign. I think I have now figured out why we don't have any kind of visible beam. It has nothing to do with the deflection. The deflection amps or all that kind of stuff, it seems to be all right. But I think it has something to do with grid and cathode. And there's a capacitor around the cathode system and the brightness that is not working. See, here's our cathode voltage, and that is actually shorted with the grid voltage, a grid system. So that means it doesn't matter how you control the brightness, you're still going to have a turned off beam. So I'm trying to load the cathode voltage a little bit so I can get the voltage a little bit down. So you can see there's a nice little spark here. But I don't really, this is just a super lazy method. The real thing is I need to disconnect everything and dig my way down to that board and find that shorted capacitor around the cathode and grid and all that kind of stuff. And I don't know if I really want to do that, but because it's going to take a whole day to get down there and see if I can figure out how to get this back again. But I really want to see those boards as well, so I might as well just go and get to it. So to get those modules out, and this one down here is the high voltage stuff. I mean, so I need to take all this out, and all these cables, they're soldered to the back circuit board here, and we got some connectors here. So, and here it's easy to see all the different colors. Okay, fantastic. We got some connectors here, but then the cable continues and it's soldered to all these. We got some sockets here. Okay, so I could unplug. I don't know, how do you think? I need to access this screw as well, and those screws up there. So to get in there, I need to figure out how to get all this off. I mean, this is not super service friendly, to be honest. And it's like really packed with circuit boards up and down and in here and down there. And I don't know. Hey, man, it's already driving me a little bit nuts. But let's see if I'm able to do this before I break down. So this is, again, the playback unit. I figured out how to take everything apart. It turns out that here at the back, we got connectors on the back plane. I don't know if you can see that, but the green and yellow wires and all that, this is the same wires that power supplies the playback unit. And you can just poke these out, and it should be fairly easy to connect all this again. And the playback unit, the reason why we have 3 DA converters, that's of course the 2 channels that is directly memory playback, so that will be the memory interface and timing for that. And then the last of the 3 BNC connectors, that one here, is the ramp output. So you can connect these, the 3 outputs directly to an external oscilloscope. And so the ramp, that is, of course, the memory position and the memory content. That will be the 2 channels that goes via all 3, goes all via op amps, and then there you have it for your external oscilloscope. And the interface cables, they are all just 1-to-1, super easy. They're just using these flat cable plugins, and they are nicely connected like that. So yes, and I think definitely the idea is you should be able to make a model without the playback unit, because you can see here, now it's taken off, and you have a smaller and more nicely compact oscilloscope. As you see here, I took out all these modules here, and they can be taken out, and then I kept all the wires here because I didn't want to screw up all my connections. So that is so it's possible to put them back again. What I really want is access to the power supply board handling the tube, cathode, blanking, and brightness control, because I believe this is where my problem is. I don't have any brightness at all because there's no cathode current, and because the cathode voltage is not correct. And how many ICs do you find in this unit? It is just amazing. All the boards, they're just so full of ICs. Wow, it is amazing. And I think about dating this unit. Let's have a little look here on my memory. So this is the storage circuit board. It also says here, store. Look at that. Those 8 chips right there. Let's go a little bit closer. That is 2102 RAM. So it's 1 bit in each and 1K. So that is our 1 kilobyte of memory in total. So each location in that 1K space is left, right. Yeah, we usually say this is normally how it is, right? With stereo, but it's channel 1, channel 2, channel 1, channel 2 in the memory. So it's this is also how it's playback again. Yeah, but I kind of like it. And you see the date is 78. So that is the age of the manufacturing of this unit, and this one is the logic for timing logic and all that stuff. Again, tons of 74. They are all just 2-layer circuit boards, and the layout quality and all that is pretty okay. Definitely done on transparent film and manual layout. You can easily see that by looking at the shape and style of tracks. Can you imagine designing stuff that way? It's just so cool. But that is how it's done. Back in the before CAD time, you actually did have CAD in 78, but it was so expensive, so you don't really see anybody use it. Yeah, you also see the corrosion here on this board. Here at the top, this corrosion is just so bad in this unit. So here's the high voltage board again. I really wanted to see if I could get this CRT up and running and get a beam on the screen. I mean, that was my minimum goal of happiness level, I think so. I don't know. Yeah, but this is just not going to happen. The capacitor here, the cathode decoupling capacitor, is not shorted, and that is what I had in mind. I see most of the voltages, they are supposed to be quite all right. But look at the potentiometers here, how badly corroded they are. Those are the potentiometers making brightness and focus and all that kind of stuff for the CRT. And I mean, with all these things looking like that, and this whole board is just corroded all over the place, and you can see, I mean, I think I'm not gonna get a beam on that CRT, so that sucks, really. I'm a little bit sad about that. I really like it when it turns out to be okay. I got my plus 3 kilovolt up and running, and it's right there. We got some hefty high voltage diodes right there. Hello. And they tried to add a little extra isolation on those capacitors used for that anode supply, but that is more or less all there is to it. We got a few other things I really want to show you as well. Have you seen my previous video, the other Gould oscilloscope, the analog one? And then you can obviously recognize this input circuit here. They just managed to make it a lot more compact in this model here. So that will be the dual field effect transistor input. And then the NPN, PNP temperature matched, temperature compensated input devices, and we got, of course, 2 of these. So that will, of course, be the analog input amplifier. Then input goes to, you see those diodes and transistors and all that here. That will be the channel select and channel chop. So what this whole board you see here, that is actually the analog to digital converter. And I should probably show you a schematic so you can see how much electronics that is needed to make an AD converter back in 1978. So all this is the analog to digital converter. We got a input amplifier, and we got sample and hold. And then all those op amps you see here, let's go down here and zoom a little bit in. All the op amps, we have only 2 op amps in each package. And that will be the scaling resistors and all that. So it's actually a flash converter. What it's doing is it's taking the first 2 bits from the first 3 op amps, and then using a very smart way to use those 2 bits and also select the ranges for the next 2 sections of the flash converters. And then combining all the bits from all the op amps, there you have it, your 8-bit of output. I think it is just amazing, that many components. And that is definitely amazing. All those transistors, all the different range amps, and and that will be all the logic. Latches and stuff. The reason for the latches, that is because they, of course, multiplex this AD converter. You have only one, and then it is channel 1, channel 2, channel 1, channel 2, and so on, right? So